Hey everyone, and welcome to another deep dive. Today we're shrinking down way down to the nano world, specifically nanowires.
Thousands of times thinner than a hair.
It's mind-boggling. And what's really got me curious is how scientists actually build these things, atom by atom. Like, how do you even begin to design something that small?
It is quite a process, yeah. But that's what makes it so fascinating. It's like having this incredible construction set where the pieces are individual atoms.
Right. I mean, we're talking about manipulating matter at its most fundamental level.
Exactly. And the research we're diving into today really gets into the nitty-gritty of that process, how to actually predict and control the synthesis of these nanowires.
Which is key, right? Because if we're talking about building the future with these things, we need to be sure we're getting what we intended. It's not like we could just eyeball it at this scale.
That's where characterization comes in.
Characterization. So like quality control for nanowires.
Exactly. Think of it like baking a cake. You wouldn't just throw all the ingredients together and hope for the best, right? You'd check along the way, taste the batter, maybe adjust the oven temperature. Characterization is like that, but instead of tasting batter, we're using high-powered microscopes and lasers.
So we can actually see these nanowires.
Oh, absolutely. Microscopy is like our window into the nano world. Techniques like SEM and HRTEM allow us to visualize these structures in incredible detail.
Wow. So we're talking about seeing individual atoms here.
Sometimes, yes. It's pretty amazing what we can do these days. But it's not just about looking. We need to analyze what we see, make sure it matches up with what we designed.
And that's where things like X-ray diffraction come in.
Right.
I saw that mentioned in the research.
Right. XRD, we call it for short. It helps us figure out the arrangement of atoms within the nanowire.
So like their internal structure.
Exactly. Every crystal has a unique diffraction pattern, like a fingerprint.
So we're basically fingerprinting these nanowires to make sure they're the right ones.
Precisely. And these techniques can get incredibly specific. We can zap a nanowire with an electron beam and analyze the X-rays that are emitted. This tells us about its elemental composition.
So if we're building with atoms, this tells us which types of atoms we used.
You got it. But we can go even deeper than that. Techniques like XPS and SIMS allow us to analyze the composition at different depths of the nanowire.
So like peeling back the layers of an onion.
Exactly. It's incredible the level of detail we can achieve. And these tools are constantly evolving, too. For example, laser diagnostics allow us to actually watch the formation of nanowires as it happens.
Wait, so instead of analyzing the finished product, we can actually see them being built, atom by atom.
In a way, yes. It's
Yeah.
like having a live feed from a construction site, allowing us to track progress and identify any issues as they arise. And all of that data can then be fed into computer models to help us understand the complex processes at play.
So we're using lasers to watch and computers to understand. This is starting to sound less like building blocks and more like conducting an orchestra, but at the atomic level.
It's a pretty apt analogy, actually. And speaking of orchestras, choosing the right instruments, or in our case, synthesis methods, is crucial.
Right. We need the right tools for the job. So how do we even begin to choose which method to use for creating these specific nanostructures?
It all starts with the application. What do we want this nanowire to do? Once we know that, we can start thinking about the properties it needs to have and the materials that would be suitable.
So like if we want to build a faster, more efficient battery, we'd need nanowires with specific properties that would lend themselves to that application.
Exactly. And different materials and synthesis methods will yield different properties. It's all about finding the right combination to meet the specific requirements of the application.
Okay, I'm starting to get the picture. So let's say we have an application in mind. What happens next? How do we go from this broad idea to an actual nanowire?
Well, let's take a specific example. How about piezoelectric energy harvesting? We talked about that earlier. The idea of using nanowires to convert mechanical energy, like your footsteps, into electrical energy.
Okay, so we have our application, piezoelectric energy harvesting. What kind of nanomaterial would work for that?
Well, for that, we need a material that exhibits the piezoelectric effect, meaning it generates an electrical charge when subjected to mechanical stress. Zinc oxide, or ZNO, is a fantastic candidate. It's a piezoelectric material that can be synthesized into nanowires.
Okay, so we have our application, and we've zeroed in on ZNO nanowires as our building blocks. Now comes the tricky part, actually making those nanowires. What are our options?
This is where choosing the right synthesis method is critical, and there are several ways to create ZNO nanowires.
So like different recipes for the same dish.
In a way, yes. Each method has its own advantages and disadvantages, its own set of parameters that we can tweak to fine-tune the properties of the nanowires.
It's all about precision and control at this scale, isn't it?
Absolutely, but that's what makes this field so exciting. We're literally building the future, one atom at a time. And CVD is just one of many tools in our nanowire toolbox.
Right. There are others like
Flame synthesis, for example.
flame synthesis. Okay, that sounds kind of intense. Is it as wild as it sounds?
It can be, yeah. But it's also incredibly powerful. Basically, we're harnessing the heat and the unique chemical environment within a flame to actually drive the formation of these nanowires.
So instead of these like high-tech reactors and super controlled environments you'd find in a lab, we're using, well, fire.
Exactly. It's a perfect example of how something seemingly simple can be used for this cutting-edge science. But of course, it comes with its own challenges.
I bet. Like what?
Well, controlling the flame temperature, the gas flow rates, the precursor concentrations, all of these things play a role in determining the properties of the nanowires.
So there's a lot of fine-tuning involved.
Definitely. And that's why even with something like flame synthesis, those real-time diagnostics and computational models we talked about earlier, those are still super important.
Right. So we can make sure things don't get too out of control.
Exactly. It's like imagine trying to tame a wild beast. We need to understand its every move, be able to predict its behavior.
So it's a constant dance between like harnessing that raw power of the flame, but also maintaining that precise control over what's happening at, what, the nanoscale.
Precisely. And that's what makes this field so exciting. It's that constant push and pull between these fundamental laws of physics and chemistry, and then our own ingenuity in finding ways to, manipulate those laws to our advantage.
I can definitely see the appeal in that. So, okay, we've talked about ZNO nanowires for energy harvesting. What other applications are out there that could benefit from this whole synthesis design dance that we've been talking about?
Oh, tons. Batteries are a big one.
Right. Everyone wants a better battery.
Exactly. We're all looking for longer lasting, faster charging batteries, and nanowires could be a game changer in that area.
Okay, I'm intrigued. How so?
Well, imagine using nanowires to actually build the electrodes in a battery. Their tiny size and their incredible surface area, it could lead to some serious improvements in storage capacity and charging speed. Plus, depending on the material you use, you can actually enhance other properties as well, like the power output or the stability of the battery.
So instead of those like bulky batteries we're used to now, we could have smaller, more powerful batteries, all thanks to nanowires.
Exactly. And it's not just about making existing technologies better. Nanowires could also open up a whole new world of applications that we haven't even thought of yet. Like, let's take biotech, for example.
Okay, nanowires in the human body. I'm listening.
Imagine this. Creating these tiny scaffolds made of nanowires that actually guide the growth of cells.
Wow, like at a microscopic level.
Exactly. This could revolutionize tissue engineering. Imagine being able to repair damaged organs or even grow new ones using these nanowire scaffolds.
Because we could potentially use nanowires to like rebuild a damaged heart or a spinal cord.
That's the dream, and it's not as far-fetched as it sounds. Researchers are already looking into using nanowire scaffolds for things like bone regeneration, wound healing, even neural interfaces.
That's incredible. Talk about pushing the boundaries of what's possible in medicine. It seems like nanowires have this potential to really revolutionize so many different fields.
They really do. And another big one is structural health monitoring.
Okay, so from rebuilding bodies to buildings, I'm all ears.
Imagine embedding tiny sensors made of nanowires into structures like bridges, buildings, even airplanes.
Okay, I can see where you're going with this.
These sensors could constantly monitor the structural integrity of these structures in real time.
Wow, that's pretty impressive. So instead of waiting for like visible signs of wear and tear, we could have these nanowire sensors giving us early warning signs of potential problems.
Exactly. It's like giving these structures a nervous system. They can feel any damage or stress and alert us before it becomes a major issue.
Wow, that could prevent some serious disasters. We've gone from tiny spacecraft thrusters to life-saving medical treatments to self-monitoring bridges, all thanks to these tiny nanowires. It really highlights the potential impact of this technology.
It does. It really shows how this technology could touch every aspect of our lives.
It's mind-boggling, to be honest.
Yeah.
But with such a wide range of potential applications and these intricate synthesis processes, There must be some pretty significant hurdles that researchers are still trying to overcome.
Oh, absolutely. Despite all the progress, there are definitely some big challenges ahead before we see nanowires become as commonplace as, say, silicon chips are today.
So what are some of the biggest roadblocks on this path to a nanowire-powered future?
Well, one of the biggest challenges is scalability.
Scalability, meaning like making enough of these nanowires to meet the demand.
Exactly. We've gotten pretty good at synthesizing these incredibly precise nanowires in a lab setting, but producing them on a massive scale, the kind of scale needed for widespread commercial use, well, that's a whole other ballgame.
Yeah. Right, it's one thing to bake a perfect cookie, but trying to bake thousands of identical cookies, that takes a whole different level of precision and consistency.
That's a great way to put it. And it's the same with nanowires. So researchers are constantly exploring new and innovative synthesis techniques that are inherently more scalable. Remember flame synthesis? That technique actually holds a lot of promise in that area.
Oh, right, because it's simpler, it might be easier to scale up.
Exactly. It's all about finding that sweet spot between precision and practicality. We need methods that can produce high-quality nanowires with consistent properties, but also methods that are efficient and cost-effective enough for large-scale production. It's a delicate balance.
Like perfecting a recipe. You know the basic ingredients, you know the steps, but finding that perfect combination of time, temperature, all those little details to get those perfect cookies every time, that's the real challenge.
That's a perfect analogy. And just like with baking, sometimes it takes a bit of trial and error, maybe a few burnt cookies along the way to get it just right.
Well, I'm definitely eager to see what delicious nanowire treats researchers cook up next. But okay, besides scalability, what other hurdles are there?
Another big one has to do with those tiny catalysts that we talked about earlier, the ones that play such a crucial role in nanowire synthesis.
Right, those nanoscopic architects. What's so tricky about them?
Well, we've identified certain catalysts that work well for specific materials and synthesis methods, but we still don't fully understand how they work at the atomic level.
So we know they work, but we don't know exactly why or how they do what they do?
Pretty much. It's like trying to build a better engine without fully understanding the principles of combustion.
Okay, yeah, that makes sense. That seems like a pretty big knowledge gap.
It is. And that lack of fundamental understanding makes it difficult to design new and improved catalysts that are even more efficient and selective.
So it's like we're trying to reverse engineer these nanoscopic machines, figure out their secrets so we can build even better ones.
Exactly. And the more we learn about these catalysts, the better equipped we'll be to really fine-tune those synthesis processes and create nanowires with even more impressive properties.
It's fascinating, all of this, but I have to admit, my brain is starting to hurt a little bit, trying to wrap my head around it all. It's like trying to learn a whole new language, but instead of words, it's atoms and molecules.
I hear you. It's a lot to process, but that's part of what makes this field so captivating, right? It's like exploring a vast, uncharted territory. We're constantly pushing the boundaries of human knowledge and ingenuity.
You're right. It's pretty incredible when you think about it. So speaking of uncharted territories, let's shift gears a bit and talk about the future. What exciting developments are on the horizon in the world of nanowire synthesis and application?
Oh, the future. Always an exciting topic. One area that I think holds immense promise is the intersection of nanowire technology and artificial intelligence.
AI and nanowires. Now that's an interesting combination. Tell me more.
Well, imagine using AI algorithms to analyze the mountains of data that are generated during nanowire synthesis. Things like real-time diagnostics, computer simulations, even past experiments. AI could help us identify patterns and correlations that humans might miss, leading to more efficient and predictable synthesis processes.
So instead of relying solely on human intuition and trial and error, we're basically letting AI be our guide in the nanoworld.
Exactly. AI can process and analyze massive amounts of data far faster and more efficiently than we ever could. And it can use that data to identify the optimal parameters for synthesizing nanowires with very specific properties. It's like having an AI-powered lab assistant that can sift through all that data and tell us exactly what to tweak to get those perfect nanowires every time.
That sounds incredibly powerful.
It is. And this is just one example of how AI is poised to completely revolutionize nanotechnology as a whole. From designing new nanomaterials to optimizing those synthesis processes, even discovering entirely new applications for these nanowires, AI is going to play a pivotal role in shaping the future of this field.
It sounds like we're on the verge of a paradigm shift. Like AI is going to unlock this whole new level of potential when it comes to nanowires, and who knows what kind of incredible innovations will come from that.
Absolutely. It's a truly exciting time to be working at the forefront of this technology, that's for sure.
It really does feel like we're on the cusp of something massive here. But let's zoom out a bit. Big picture time. What does this future actually look like? What kind of world are we building with these atomic building blocks?
That's the big question, isn't it? The million-dollar question. And, well, we don't have a crystal ball, but the research gives us a glimpse into some pretty transformative possibilities.
Okay, so paint me a picture. What does an AI-powered, nanowire-driven future look like?
Well, let's start with energy. Imagine a world where energy is abundant and clean, accessible to everyone. Nanowires, with their ability to capture, store, and convert energy, they could be the key to making that a reality.
So no more reliance on fossil fuels.
Yeah,
No more worries about energy scarcity or climate change.
that's the ultimate goal. Imagine solar panels so efficient and affordable that they're everywhere, integrated into buildings, windows, even clothing. Or batteries so powerful that electric cars could travel thousands of miles on a single charge.
It sounds almost too good to be true, like something out of a science fiction novel. But where does AI come into play in all of this?
Well, that's just it. AI can help us design these next-generation energy technologies. We can use it to optimize the nanowire structures at the atomic level, maximizing their efficiency and performance.
So it's not just about building a better battery, it's about using AI to design a completely different kind of battery. Yeah. One that pushes the limits of what we thought was possible.
Exactly. And it's not just limited to energy. Think about the medical field. We've already talked about using nanowires for things like targeted drug delivery, biosensing, and tissue engineering. Imagine the possibilities if we combine that with the power of AI.
Right. Like those nanoscale scaffolds we were talking about earlier, using them to grow new organs or repair damaged tissue. It seems like something out of a sci-fi movie, but it's becoming more and more within reach.
It really is. And AI is going to play a huge role in making those things a reality. Imagine designing personalized nanomedicines tailored to an individual's genetic makeup or creating intelligent implants that can monitor and respond to changes in the body in real time.
The possibilities are incredible. But it's also a bit, I don't know, a bit overwhelming when you really think about it. This level of technological advancement, it comes with some big questions, some ethical considerations that we need to address.
You're absolutely right. With any powerful technology, it's crucial that we develop and use it responsibly. We need to carefully consider its potential impact on society and the environment. It's a conversation that needs to happen alongside all the scientific breakthroughs.
Well said. It's a reminder that as we explore these new frontiers, we need to keep our ethical compass firmly in hand to make sure these advancements ultimately benefit all of humanity, which I think is a perfect note to end on, actually.
I agree. It's been great exploring all of this with you.
It really has. To our listeners, thank you for joining us on this deep dive into the incredible world of nanowires. We hope you learned something new and exciting today. Until next time, keep exploring.